Hi friends, let us continue our discussion on finding the minimum spanning tree. Some sessions earlier we had used the Cruxell's method for finding the minimum spanning tree because it used the disjoint sets, and that time we were working on disjoint sets, so we had seen how disjoint sets help in finding minimum spanning tree. Now we are working on the converting a graph into a tree through what is called search, especially the depth first. So here the Prim's method mainly works with a depth first search algorithm. So how does that work? It's a greedy method, makes use of a depth first search, and it's a greedy method. That means at every step takes a greedy possibility. So whatever is the best possible at that time, only that time will be considered. Okay, let's see the whole method begins with the edge with the smallest weight, and is in this the smallest weight is between 1 and 6, which is 10. Therefore our whole story begins with 1 and 6, so that is 10. Now it can be 1 to 6 or it can be 6 to 1, whatever way you like, you take it. So you can extend it either from 1 or from 6, or the endpoints are used to extend. And a linear structure is tried to be formed through extension of the ends. Okay, let's see if I could extend from 1, it can go to 2, and the weight is 28. And if I extend from 6, it goes to 5, and the weight is 25. And of course, 25 is a better choice than 28. Therefore, we extend from 6 and go to 5. Now from 5, what all options open up? So there is one option in the second step that 1 to 2 can be used, or 5 to 4 can be used, or 5 to 7 can be used. So this is 22, 24, 28. Therefore 22 happens to be a better chance. So we extend this 22. So that ends that now we are having 1, 6, 5, 4. So from 1, if you want to extend, it can go to 2. From 6, both conditions already used. From 5, we can extend to 24, and from 4 we have 18, we have 12. So smallest of all of them happens to be 12. So 12 spins the race. So the connection from 4 to 3 is done. Now we have 1, 6, 5, 4, 3, and we can see what all possibilities are there. So from 1, still there is a chance to go to 2. From 6, nothing is there. From 5, you can go to 7. And from 4, you can go to 7. And from 3, you can go to 2. So 1 to 2 is 28. 5 to 7 is 24. And 4 to 7 is 18. 3 to 2 is 16. So 16, 18, 24, 28. Therefore, 16 wins the race, and hence that gets the next chance. So now 1, 6, 5, 4, 3, 2 are there. From 1, 24 is still contesting. From 5, 24 is still contesting. From 7, 18 is still contesting. And from 2, 28 as well as 14 are contesting. And if you look at this 28, 14, 24, 18, then 14 wins the race. So we get 14 here. So how many are added? 1, 2, 3, 4, 5, 6. How many nodes are there? 7 nodes are there and 6 edges. So if n is number of nodes, so n minus number of edges will be required to create a spanning tree. And you try to add any more. So the next possibility would be 18. So if you try to add 18, that means 7 with 4, it forms a loop. Therefore, you cannot call it a tree. Or 7 to 5 will form a loop, or 1 to 2 also will form a loop. So anything greater than n minus 1 edges, if you try to add, it no longer remains a tree. It becomes a graph, which is not a tree because it contains loops. And because we are using a greedy logic, and we find that the algorithm finds the spanning tree, which is hoped to be the smallest possible. So if you want to include 7, so let me start one by one. Are we at the best? So if you want to 1, then either 10 edge should be there or 28 edge should be there. So we have using 10 edge. That's okay. So we use 10 edge. So if you want to see the for 6, there is only one option, that is 25 to continue. And for 5, there were two options, 24 and 22. Yes, it has taken the smallest one. 4, it was having two more options, 12 and 18, and it has taken 12. And 3 had only one option, and 2 had two options, 28 and 14, and it selected 14. So that makes the tree 10, 25, 22, 12, 16, and 14. Yeah, greedy method works, and that is exactly the same spanning tree we had found using Kuxel's method also. So that's how we can solve this problem analytically. And we have been using our intelligence, and we are working with the graphical method. That means all the nodes are visible at the same time, which machine cannot do. And we have intelligence, so a lot of things are done through that intelligence, which our machine is lacking. Therefore, if you want this whole activity to be done by the machine, then you need something so that machine can understand. So you need to work machine friendly, whereas whatever we did till now was human friendly. Now the issue is how do you find this human machine friendly way from whatever we know that's our human friendly. So what did we do? So we looked at first step was find the edge having smallest weight, and from there start expanding in all possible ways, and whichever way expansion is simpler, continue that. And because we are working on greedy logic, so converting this into machine friendly, so we just look at in our coming sessions step by step and try to create a full-fledged logic so that a machine can clearly understand our intention, and also we can make our machine to understand the logic how to solve this problem. So keep watching. Thank you.